So this is the, we have done that this is given as energy. So fluctuations in energy, when you plot that, lo and behold, it's a very good Gaussian, amazingly good Gaussian. Another surprise of nature. And then the width of that fluctuation is the specific heat. And that is the spring constant in my, so why it becomes Gaussian? There are two reasons of that, and I'll give first the mathematical, then the physical, or both can be considered mathematical. But before I go into that, look at this functional form. Why? Now remember, E average is the value at the minima, and that is a macroscopic quantity, that the average energy of the system. So system must be minimum with respect to the average energy. So I now, first derivative will go to 0. So second derivative will be this quantity, which is the sigma square, which is the specific heat. So this is the reason why this, one of the explanation is that the total energy of the total energy of the system, or the fluctuation in total energy, is Gaussian. There was a question asked, I think yesterday or day before yesterday, and this is the answer to that question. Second important explanation that comes from a very profound theory of probability that I described, I think in my third lecture, and I think in my book also I described that quite a bit. That's called central limit theorem. Central limit theorem says that if your total observable, let's say x, capital X, is a sum of a large number of small parts, and if there is a weak correlation, correlation is allowed, there is a correlation but the weak correlation between them, then the sum is Gaussian. This is called central limit theorem, which is an exceedingly important part of statistical mechanics, and I think I have discussed it a couple of times in my book, and I think in my third lecture we discussed it, and this is what Rajorshi keeps complaining, that how many times we teach the students forget. But this you should not forget. There is a strong law, there is a weak law, and I told you mathematicians are not given, this was also the person who worked on it, theory of errors, and all these things goes back to Gauss. Gauss, I think, had one of the proofs long time ago. I think Gauss was after Shakespeare, I think somewhere 1600 around that time, or little later than 1600. I used to know all these things, but forgetting. So then central limit theorem says, if I have something x, which is sum over xn, n is large number, and then xn are weakly correlated, then the px, an amazing theorem, just amazing theorem, that this is the central limit theorem, perhaps one of the most, and I told you mathematicians are not given to give big names. We chemists and physicists, we just mutilate and insult the English language, but they have a very rarely one thing like fundamental theorem of algebra. Whole algebra is based on that theorem, whole complex analysis. This is the whole, much of probability theory is based on this central limit theorem. The central limit theorem says that this is Gaussian. One of the ways you can do that, which you take up any book of probability, they will do in terms of binomial theorem. Toss a coin or take a dice, then you will find the sum will become, go on adding 3, 6 if you are throwing a die, and then you find that is Gaussian. Now all of you who do molecular dynamics or Monte Carlo simulation use this at very early stage of your simulation. Now tell me where? Not quite, Baba. you sample from a Gaussian distribution. How do you create the Gaussian distribution? You take random numbers, we call I seed, call random numbers, add the random numbers. You know, if you do not use a package like our days, we used to, there was a function in Fortran called rand, but we used to write our own code usually because we are always pseudo random number and did not Gaussian correlation. We used to do it ourselves by doing you can play around a little bit and make it much better. And sometimes we used assembler language and to make it more uncorrelated. However, one important thing, you should do it yourself. You call a random number, call it only 12 times, add them up, you find the sum of the Gaussian. All it takes is 12. So I don't need to go to infinity. Strictly speaking, it has to be large, but in real world, just 12 gives it Gaussian. This is one of the reasons many things in observed properties in nature are Gaussian. Okay, so then here is a table. Actually, my student made it today very quickly from the book. But here, energy at constant volume, then CV, response function. So, Z the thermodynamic quantity. So, there are actually three things one should have had here. One is the perturbation, one is the fluctuation, and one is the response function. Or I would probably have done perturbation, response function, then microscopic interpretation. This, as I told you, it is a profound result of statistical mechanics. Perhaps one of the most, I won't say the most, but one of the most profound result of statistical mechanics, and it's amazing that it tells you what is specific heat. Okay. Then Cp is that of enthalpy, then volume and number density give you isothermal compressibility, and you have to work in different ensembles to get that. NPT will give you volume fluctuations, okay, and grand canonical will give you number fluctuation. Please listen carefully. This comes from NPT, isothermal isobaric. This comes from grand canonical ensemble. You can calculate the fluctuations that give you both give you isothermal compressibility, and they give you exactly same result. You can do the simulation here in one ensemble, another ensemble, you will find they're exactly the same. Okay. Magnetization is the external magnetic field, magnetization is the response, and this is the response function. Then I put an external electric field, this is the response polarization, and this is the response function, dielectric constant. So all the time experiment is measuring dielectric constant without really knowing what the hell they are doing. But it is the theoreticians' responsibility to understand these things, and that has happened. That's the way it has happened. The experimentalists much of the time need to work extremely hard to get a result, and they really have not much time for this theory and all these things. And you will find a kind of disregard for us, which is painful, but that's the way it is. Okay, so now there are certain very interesting results that I want to tell you, and that you should know. Here is the specific heat, ice, then these are solids, ice, aluminum. Look at this. Now you expect solid to have less fluctuations, and their specific to be same, less. That indeed there is less. Okay. Now look at the things, liquid, look at that. Ethanol is so much bigger, but water has almost twice the specific heat. Why? I'll come to that. Liquid nitrogen, this one, benzene, this, benzene is so much bigger than water, but much small. Mercury is really has much less specific heat. Hydrogen, partly because there is an anomaly, because they have the ortho-para equilibrium. As a result of that, they have a very large fluctuations. Helium has quantum effects in it, which allows it to really explore much larger energy fluctuations. But look at that, as you would expect, this is less, this somewhat more, and where this is little bit more. So now it is a standard questions we ask, why has water specific heat is that of more than twice of benzene, which is bigger than water and also bigger than ethanol. So there is a question I am now asking you, explain why water has such large specific heat. And that is very good for you, otherwise you would die of fever, you know. Our body, we are very lucky that water has large specific heat because 70% of our body is water. Otherwise your protein, if temperature some comes outside, your protein would become, temperature of the body will rise and your protein will become unfolded and you die. Now you need to tell me why and how water has such a large specific heat. Right, it is due to hydrogen bond. There is a bit more than that, this is a good beginning. Hydrogen bond, certainly. If hydrogen bond not there, then water would not be liquid first of all. Because it is only atomic 18. Much heavier things are gas, but water because of hydrogen bonding. So it is hydrogen bonding. But what next? Ethanol also has hydrogen bonding, don't forget that. Ethanol forms 3 hydrogen bonding. Through oxygen, 1 through hydrogen. Water forms how many hydrogen bonds? 4. 4 hydrogen bonding. Still, answer is not there. Come on. Yeah, that you are saying this is a semantics. You are just putting the same thing in words. Okay, we will not be able to waste too much time here. That the reason is that because of hydrogen bond, there are a lot of excitations in the system. If you do the normal mode analysis, that means you can freeze water or take the temperature out and then do a normal mode analysis, means you calculate the density of states, or you can even take water in a little what temperature and do the velocity time correlation function and do a Fourier transform. That will gives you the oscillations and as a peak. You will find water has 3 pronounced peaks. One is about 50 centimeter inverse, that is because of rattling, but there is this peak at 200 centimeter inverse, which is hydrogen bond excitation. Now tell me, what is 1 kBT? Thermal energy, how much in centimeter inverse? (300 Kelvin), how much? 206 centimeter inverse. 1 kBT is 206 centimeter. You might look surprised, but that's what it is. So 1 kBT, 300 Kelvin is 206 centimeter inverse. And hydrogen bond excitation, the network is vibrating like that. That's a Raman active mode. That is 200 centimeter inverse. Then there is a libration, which is about 600 centimeter inverse. So water, because of the hydrogen bonding, has all these collective excitations. So when you raise the temperature, then all these excitations get populated. So before temperature goes up, you need to populate them. And as a result of that kind of extensive network, not in ethanol, because the ethyl groups is hydrophobic. So there is a local order, but this kind of extensive network we call hydrogen bond network, that is so peculiar of water, that is not there. So this is a beautiful slide that I think I'll give it to them to put it on the book. Okay, so now this is what I have been talking, free energy expansion and the response functions. This, because of the minimum, our A quantity X is either pressure or Y, then this is 0, but then the expansion becomes that in free energy, and these are the expansions. In energy fluctuation is a specific heat, volume fluctuation, compressibility, and if I have the fluctuations in the system is the magnetic susceptibility. So what is important, these free energy expansions who free energy second derivative are these response functions. Those are the same functions that give you, that tell you how much a system going to react. And I gave in the example of water, it is essential for you and your body that water has large specific heat, otherwise you die off. And exactly that these quantities are the ones which are most important constitutive properties of a material. They are the ones which measured in the very beginning. Okay, okay, this is the end. So my students are fond of cartoon, so they say that I am trying to fluctuate because it's certain life must have some responsibility. So they are not great cartoons, but statistical mechanics is such a difficult subject, it's good to have some cartoon than no cartoon. So this is a picture of Einstein I really like. So this is a chapter which you have to read, and again the same kind of things that I have been talking here, that how the same thing repeating again, and the equations from there, but there are a lot of very nice things that are discussed here and quite a detail, because this is my favorite chapter. So energy fluctuation, specifically the derivation is given here, is a little better than what is given here. You can see the derivation in full glory. Sequence is little different from what I told you here. Then the fluctuation in other response functions, full derivation is given here. Okay, the full derivation is given here, and these both Grand Canonical and NPT ensemble, and then there are some very nice system size dependence on fluctuations that we just discussed. Yes. No, non-linear phase transition. All free energy is minimum with respect to all thermodynamic properties. Whatever you choose. As Einstein showed, there are two independent variables. So you have to be like if you look Einstein's statistical physics, then somewhere around chapter, I think Landau-Lifshitz, the old second edition that I studied, somewhere in after 30 or 40, around that, he had this, Landau has this chapter on fluctuations. And there he discusses this, that Einstein selected two independent variables, entropy and volume. And as I told you, he also discusses pressure and temperature, Landau, because there is connection with the hydrodynamics and discussing very important experimental results, which can also be through entropy and volume, but it gets very complicated. Pressure and temperature is a better variable. The Rayleigh-Benioff spectra, the three peaks, that is explained by hydrodynamics. Okay, so it is minimum. Only thing you have to make sure that you have the two independent variables. Do not take two dependent variables, then you screw up. Only near a phase transition, this spring constant just goes. That's why it's like here. So long I am here, I am stable. But when I come here, it is no longer stable. That exactly happens in phase transition. The system falls out of the cliffs. And it falls out of the cliff, this quantity just becomes like that, flat. Do we call it softening? Very important term in physics. Softening of modes. Yes. Absolutely. I don't know why you are confused. Free energy has to be minimum, otherwise it's not stable. It has to be caged in. That's why I'm talking of spring constant. Just take a spring, do that. The spring comes back, right? So you are applying a force, spring getting elongated. Who determined? I could have put that also. That I give a force, elongation is L. That is the omega square x. So that has to be. This is a good question, but you have to think and make yourself believe, because these are the fundamental and exact results. That's I told you in book I had, and I wish I kept it. That is really statistical, very significant result from statistical mechanics. Explaining your high school thermodynamics and physics is coming from this chapter. We don't question it, but we should actually think about it, because it's just too fundamental to ignore. Otherwise, there is no point of doing science. This is really beautiful. Okay, so this is same thing I discussed. These probability distributions, and now going back to different ensemble, microcanonical, grand canonical ensemble, and the maximum means now omega has to be maximum. Okay, and then partition function has to be, I told you partition function is the quantity that is maximum, and I explained in the morning why partition function is maximum. Partition function is maximum because e to the power minus e by kBt, as I said, or omega is that particular state is selected which has maximum number of microscopic states. And then this is what we discussed, and this is what we discussed. There is a question actually one of you asked why it is Gaussian, and this is the reason why it is Gaussian, it will be at fundamental level, and the distribution of specific heat and thermal conductivity, all these things we discussed. So, but I would strongly recommend you take a look into this book, this my book, because I don't think there is any other book that has discussed this in so beautifully, except I think Pathria, statistical physics, but then he does not connect it to this water specific heat and the kind of things we physical chemists or chemists deal with. That's not their cup of tea. They will go to liquid metals and not interesting. As I said, mercury is specific is how much, 0.2, solid specific heat so small, except when they go to phase transition, their specific heat diverges. Order disorder transition. Order disorder transition in aluminum and manganese undergoes order disorder transition, but that because you have these multiple ways to arrange things with different energy. So, a binary alloy undergoes a spectacular phase transition. Anything else? We'll next class Monday we'll start with the applications of the partition function and describing some way and getting some very important results which are even today used in drug design or all kinds of thermodynamic packages from NIH and other people use what will be very I never knew that in drug design we use the Sackur-Tetrode equation which is derived with monatomic gas, ideal monatomic gas.